Hello everyone. Um, in this video, I'm going to walk you through this question, SQ5. It is one of the questions, actually the last question of our special antenna exercise. So you are given a vertical half-wave dipole. The length is quite long, half of the wavelength, almost half, right? It is mounted above the ground. Uh, the spacing here is about 0.15 lambda. I mean the spacing between the lower end of the antenna and the ground band is 0.15 lambda. And the first part of the question asks you to draw the image antenna together with this one and detail all the polarity of all the antennas. So you need to identify, right? For example, if the current direction is going upward, and then in the lower one, the image one, there should be a current direction as well. You have to identify it. And the second part, determine the spacing. That's easy. You just need to count the spacing between the midpoint of the antenna and the midpoint of the image antenna. And determine the far field expression. Yeah, this is also easy. And determine the angle of maximum radiation. It shouldn't be difficult. And determine the angle for the first node. So you need to equate the array factor to 0 in order to get the first node. And finally, the directivity. And I'm afraid I don't think there's an easy way to calculate the directivity. So I will just leave this part of the question. I will leave this part of the question. Yeah, I don't think I have enough space to overcome it. So yeah, the procedure is quite long. So I will just go through from part A to part E. Then uh, my job is done. Okay, I'm now going to give you the let me see. So we need to go up a little bit. Okay, so I think we can start now. But there's a live image. Let me just make it brighter. Okay, so we can start now. Yeah. So first of all, SQ5 we have an antenna like this. And you have a ground plane. You have the ground plane. And the spacing here is about 0.15 lambda. The length here is about 0.4781 lambda. So obviously there will be an image antenna here. Yeah, too long, too big. Let's make it smaller. So this is the image antenna. And the length here is also the same. Uh, Now, assuming that the current is running upward, and as a result of the current, you will produce a electric field, circular electric field. The electric field somehow go through the surface of the ground plane. So that would end you up with a tangential electric field. But the physics, the law of physics dictate that tangential electric field is always zero. So this means there will be a counterbalance electric field originate from the image. So in the image, there will be a electric field circulating in clockwise direction as well. So as a result, you will also produce to produce this electric field, there must be a current running upward in the image antenna. And I can for sure the image polarity will be exactly the same as the real antenna. So this is real and this is image. So first part of the question done. Now the second part of the question asks for the spacing. How are we going to calculate the spacing? My suggestion here is you count from the midpoint. You calculate the spacing at the midpoint. So according to the diagram here, you get dz, and then the upper one, it will be 0.4781 divided by 2 times lambda divided by 2, and plus this one, 0.55 lambda, and the whole expression multiplied by 2, and you will get the value. From my calculation, I got 0.7781. So you might just assume it's almost equals to 0.8 lambda. So, okay, part C of the question. Part C, uh, you are having one real antenna slightly above the ground, but the image antenna will also contribute to the far field, and this is where the problem of the question is. Now work out the work out the antenna array as a result of two identical antennas with exactly the same excitation, because this is what we get. So the base will be the same. Now, what I'm going to do is I'm going to draw this line here, yeah, and then draw this line here. So this is R2, R1. R1 is the pathway of representing the direction of the electric field going towards the target. And then the R2 here, and the midpoint here is R. So we get R 1 is equals to R minus, sorry, plus d cosine theta, where theta is the angle here, the angle here. D Yeah, we should use d divided by 2. So this means about uh, d divided by 2. We should use d divided by 2. Okay, and for the lower one, we will have the same, but minus. So if you do it very carefully, you will get the AF based on the AF palm, let's say AF palm, based on the isotropic measurements, is going to be, yeah, this is one way we can do it. This is one way, yeah. E, and then hello, but this is not a good way, to be honest. Why don't we just do it straight? We are going to substitute to the uh, main expression. Remember, the far field of an individual half-wave antenna is given by 3 and I know. Yeah, it's in my notes. JK R and then 2 pi R. And then we have got a big chunk of expression. Cosine, and then KL divided by 2 cosine theta. The length here is even cosine theta, and then minus cosine KL divided by 2. Again, at the same time. And divided by sine theta. So what I want you to do is we will do this. We will say E1, the E total, the total electric field will be contributed by the lower antenna and the upper antenna. So E1 plus E2. E1 is the electric field going through the pathway of R1, and it is the electric field contribute by the real antenna. Where E2 is the SQ going through the R2 pathway. It is the SQ due to the presence of image antenna. So both antenna can be calculated using this expression. So we can do this. Yeah, I'm going to deal with the terms that is independent of all of us. So cosine KL theta minus cosine KL divided by 2 and then divided by sine theta. Now, the next one will be E minus JK R1 divided by R1 plus because both antenna have the same direction, the same polarity, K R2 and then R2. So this is how we construct the array vector. And if you are familiar with the process, you will know that this will eventually end up with sine KL divided by 2 and then sine theta. Yeah, very awkward. Now, this one, yeah, if you are familiar with the process, you will end up with JKR divided by R. So this is the first term. The second one, it will be equals to 2 times cosine uh, um, K D divided by 2 and then cosine theta. Yeah, if you are familiar with this, then you know what I'm talking about. Now, in part C, there is another. Yeah, first of all, I will put the numerical value here as well. KL divided by 2. K is 2 pi over lambda, and the 2 will remain. And then L is almost 0.5 lambda, so lambda divided by 2. So from what I can get here is almost pi divided by 2, yes? So I can simplify the expression here. So E of t is equals to J and theta and then IO and then the 2 here will be cancelled out, so divided by pi. And then the expression here, KL divided by 2 is almost equals to pi over 2. Now, cosine KL divided by 2 is cosine pi over 2. Cosine pi over 2 is 0. So that's how we simplify the process. And then here, divided by sine theta. And we have this term divided by, sorry. Now, here, you got almost 0.8, yeah? and I am going to approximate it. Uh, so 2 pi over lambda, and then 0.8 lambda, and then cosine theta. So this is the expression. Lambda and lambda get cancelled out. And then here, so 1.6 pi, 1.6 pi. I will just write down straight away. Yeah, I need to spare the space. Yeah, lambda here get cancelled out. 2 and 2 get cancelled out. Uh, we will get 0.8 pi, yeah, 0.85, 0.85, sorry about that. 0.8 pi cosine theta. So this is the final expression of the electric field. This is a ray vector. The second part of the question, they ask for the power density. Oh, that's easy. You just need to take the square all the time. Oh, so um, I'm going to continue from here. So the radiated power will be equal to, and then theta, and then remember, yeah, this is arrow, yeah, the power should be moving forward. So here the theta will be gone. So J and J square, nothing. So I know square and divided by pi. And then there is no magnitude here. The magnitude will be always one. So you only need to care about this one. So 0.8, is there any pi here? Yeah, there is cosine theta. Okay, so now we will continue and we will solve. This is part C, and we will solve part E as well. Part D, the major loop. Yeah, by the way, I think it's better for me to make it clear to you so you can see the whole screen. The major loop. So you have two functions that is related to theta. So in order to get the maximum, you need to have this value has to be 1. This value has to be 1. So cosine for E of t to be maximum, we set this guy cosine 0.8 pi and then cosine theta. We will set it to 1. This is the maximum value of cosine theta. And this means 0.8 pi cosine theta will be equal to pi over 2 or 3 pi over 2. But we want to find the major loop. And theta will be equal to 2 times 0.8. So it's 1 over 1.6. 1 over 1.6. Let's just do some calculation and see what value I will get. A cosine 1 over 1.6. So 51 degrees. Theta will be equal to 51. And the next part of the question, but according to the question, it's 91. So I presume there is another node, maybe contributed by this one. So let's try this. Let's try this. So pi over 2 cosine theta has to be equal to 1. So pi over 2 cosine pi over 2 is equal to pi over 2. Okay, in this case, theta here can be 0 or 180 degrees. So none of the angle here makes sense. So I don't know. Now let's take a look here. Let's take a look. The maximum radiation 90 degrees. But from what I can get is 0. Okay, let's continue. Part E. Let's try part E of the question. Part E, we need to find the first node. The first node will be, we can say either this one to 0 or this one to 0. So we can try both. And 0.8 cosine 0, and this will be pi over 2. I know now. Yeah, in this case, I got a mistake here. It should be pi. Pi. If it is pi, then here will be 0.8. No answer. There's no solution at all. Doesn't make sense. Maybe you're just 0. 0 is probably the best. So you just 0 and in this case 90 degree. Okay, correct, correct. Question part D of the question is correct. 90 degree. So we will cross out this part. Part E, we will have here point A cosine theta and then 1/2. Or this means cosine theta is equal to 1.6. And in this case, as before, we know theta is 51 degree. Okay, done. And how about this one? Do you think this one will have any contribution? Maybe, yeah, we can try. So let's say cosine pi/2 cosine theta equals to 0. And in this case, if it is 0, then pi/2 cosine theta is equal to pi/2. And then theta will be equal to 0. Yeah, it doesn't make sense. Or 180 degrees. So these both answers can be rejected. So reject, reject. So this is the answer, and this is the answer for part D of the question. Okay. I think as far as I know, our job is done. And I'm not going to calculate the directivity. Thank you. If you have any further question, please leave your question to the comment section. Okay, bye bye.